Okay, so I can start now. Again, my name is Yasser Mohammad. Thank you for being here. I want to speak today about the Generalized Bargaining Research Program, which we are working on recently, and to introduce a specific negotiation mechanism we have designed called the tentative acceptance unique offers that I think provides many advantages over existing mechanisms. So let's start. What is a negotiation? In a negotiation, we have an agent. In this talk, I use agent and negotiator interchangeably, and protocol and mechanism interchangeably. So we have an agent that represents some institute, and the institute has some utility function or preferences over some set of outcomes that can happen in the world. And to make these outcomes happen, they need to negotiate with another agent representing some other institute. And to do the negotiation, they need some protocol. Who can do what, when? So that's negotiation. And to achieve good negotiation, we need to understand what we need, what we want, that's understand ourselves, and we need to understand our partner. Again, I use partner and opponent interchangeably. I don't like the word opponent, but it's the word that's used in literature all the time, so I have to use it. I prefer partner because if it's really an opponent, it's not really a negotiation. So in negotiation, you have both cooperation and competition. They need to achieve some outcome that is good for both of them. If it is not good for both of them, none of them will take it. So they need to cooperate to find a good outcome. So they are collaboratively searching over the outcome space for a good outcome, but there can be value division because their preferences or utility functions usually do not match. If they match, they don't need to negotiate. There are many applications for automated negotiation that are starting to pop up everywhere in business, something like smart contracts, smart resource allocation. We see it in IRIS this year. Just a few days ago, there was something about automated negotiation used for routing different vehicles on the platform of factory. So there are applications that are popping up everywhere. And one of the main reasons that many businesses are now moving to use AI for their operations, and these AI agents need to agree on things without sharing information. So to define a negotiation, we define a scenario, which is who is negotiating with what, with whom, about what. That is what the negotiation scenario is. And as we said before, we need a protocol to define who can do what, when, and a strategy that defines what every agent is doing. So what do we have now? What is the state of the art? So we have rigorous guarantees of negotiation performance in unrealistic. So we know what happens if both agents know as a common knowledge the preferences of each other. So we have the Rubinstein bargaining result, the Nash equilibrium, and the Nash bargaining game. We have the greedy concession algorithm, which is the most recent thing that is related to that. So in unrealistic cases, we know what should happen. And in most of these cases, negotiation wouldn't even happen. It would be one step, everyone will agree, everything will be happy. Everyone will be happy. But for realistic cases, like for example, the very common case that every agent knows its own preferences, but it doesn't know the preferences of the other partner, and it doesn't know the strategy they are using for negotiation. We don't have any rigorous results on this area. We only have heuristics. Many heuristics, very good heuristics, but heuristics. And as a result, in most cases, people are focusing on the strategy, trying to find a good strategy for a simple protocol, as simple as possible. And I'll describe the most commonly used protocol, the alternative offers later. There is some research in trying to find other protocols that have better results, that achieve better results, but usually these protocols are mediated. They need a third party. And in the cases I'm interested in business operations, we don't want a third party. A third party is bad. We want negotiation to happen directly and with as little exposure of information as possible. So third parties are not a good thing. And for a long time, we thought that the only option in this case is alternative offers protocol. the simple bargaining protocol that I've described. And what I'm trying to convince you today is that no, there are other options, and we didn't look. That's why we didn't find anything. If we look, maybe we will find even better protocols. And I will propose even one, the very first thing that we try to do in this area. So what we want is a simple protocol that works in realistic cases and with some rigorous guarantee on performance. I'll describe what this means exactly later. And we want as little intelligence in the negotiator as possible. We want the intelligence to be in the protocol so that a very simple negotiator should achieve good result. Something like what happens with victory auctions in auction theory. So we don't need any intelligence in the bidding policy. The intelligence is in the mechanism. So that's how my talk will go. I'll describe automated negotiation, what it means in general, negotiation with complete information. I'll give some of the results we have. I'll go over that very fast. Then I'll speak about the alternative offers protocol, the MED protocol that's currently being used widely for automated negotiation. And I'll speak about what is wrong with that. Then I'll describe our research program for finding other mechanisms that achieve better performance than alternative offers, and I'll describe a specific one, the tentative acceptance unique offers mechanism. I'll also give some little evaluation that we did recently. So what is an automated negotiation? As we said before, it's defined an automated negotiation scenario, defines the whole set, and for automated negotiation to happen, we need a set of agents, so a set of agents, and a domain. What we define the domain as 3 components. The outcome space, that's a set of all possible outcomes, and I always assume that there is an outcome called phi representing disagreement. And the preferences tuple, that's a tuple matching for each one of the agents as specific preferences representation. So the preferences can be either cardinal or ordinal, so you can have a utility function, or you can just have an ordering over the outcome space. And this can be a partial order. So that's the preferences tuple. And this is not known to agents. I don't know my own preferences either. The only thing they know is the information set tuple. So the information set tuple is telling every agent what is the known information about the preferences of all agents, including itself. In most cases, we assume that my own preferences are included in the information set tuple. But that's not always the case. For example, in elicitation research, we don't have this assumption, or negotiation under uncertainty. Then we need a mechanism. And the negotiation mechanism defines how a set of strategies will, taking this information, will behave. It describes what are the actions available to strategies at every point of time. So, given any set of scenarios defined this way, we can have a game. And the induced game, given a set of scenarios, is a very simple one. Nature moves first. It selects a scenario, which means an assignment of the outcome space, the preferences, and information available. And then agents play according to the mechanism. And at the end, each agent receives the result of the negotiation, either the utility of the output. And the negotiation output, if it is disagreement, phi, so everyone receives what we call a reserved value. Otherwise, they will receive the utility of the outcome they agreed upon. Okay? So we have a game, and if we have a single scenario, that is the complete information case. If we have a single scenario, then it's a simple game like that, and we know a solution for this in some cases. So some of the definitions that I need for this talk are the following. I need to know to define the rational outcome set for an agent. These are simply the outcomes that it would agree to on, outcomes that are better than disagreement. The rational outcome set for the whole scenario is just the intersection of all the rational outcome sets. We always want our outcome from the negotiation to be in this set. The irrational outcome set, of course, is the remaining of the outcome space, and the irrational for an agent and for the scenario. Then we define something we call win-win deals, and win-win deals are simply outcomes that are strictly better than disagreement for someone. Okay, they are strictly better than disagreement for someone, and they are not worse than disagreement for the others. They are always in the rational outcomes. Some people actually, in some cases, we just use win-win deals to mean outcomes that are in the rational set without this strict requirement. But in this talk, I'll always assume that in a win-win deal, at least one agent can benefit from the negotiation over disagreement. The Pareto frontier is the set of outcomes that dominate every other outcome. Okay. Sorry, that is outcomes that cannot be dominated by any other outcome in the outcomes. So that is one of the simplest games possible, the Nash bargaining game, which is a single-step full information bilateral negotiation. The outcome space is any value between 0 and 1, so we have a continuous outcome space. And the two utility functions are defined as follows. So for each agent, you have a utility based on the outcome of the negotiation. And the way the protocol runs in this case is that each agent will announce a value between 0 and 1. If the sum is less than 1, each one receives what they announce. And if the sum is greater than 1, they don't receive anything. That's a disagreement. So we always have, for these kinds of games, what we call the disagreement point, which is disagreement, meaning that every agent is receiving its reserved value. In this figure, we show the utility of one agent on the x-axis, the utility of the other agent on the y-axis. And these are all the possible outcomes in this game that are valid. So the outcome must be on this line. And sorry, these are the Pareto, sorry, that's the Pareto frontier, of course. These are the best possible outcomes, but you can have outcomes that are worse. When we have complete information, we have different ways to define the solution. So there is a Nash point, the Carlyle point, and there are other solutions, and all of these were achieved by assuming a set of axioms about what we want to be sure about for the agreement, and from them finding a fair solution to the game. In all cases, there is no need for repetition. In the Nash bargaining game, the protocol itself does not allow repetition. So what if we allow it? That's what Rothenstein did. They allowed repetition, so agents can exchange offers. I can send you an offer like normal haggling, and you can reply by another offer until we agree, or some time condition expires. And the time constraint on each agent can be different. So one agent can be more in a hurry than the other agent. Okay? And the main result that Rothenstein found is that there is a subgame perfect equilibrium for this game. And this subgame perfect equilibrium ends in a single step. There is no need for exchange. Because each of us knows the utility function of both agents. It's common knowledge under this, in this case. We don't need to actually negotiate. There will be one offer that we can calculate based on our timing constraints, which we both know. And the first agent will offer that, the other agent will accept. That's subgame perfect equilibrium. Okay? So we have results with complete information games. But what are the results that we have for incomplete information games? We have some, but not as strong as this. We don't have any guarantees on performance. The most commonly used protocol for negotiations with incomplete information. What I mean by that are cases in which the information set does not equal the preferences. Is the alternative offers protocol, which is actually very simple. All negotiators sit in a circle because that works for both bilateral and multilateral negotiation. And some negotiator begins, and until some time limit, which is imposed from the protocol, is met, either a number of rounds or some whole time, we receive one offer from one negotiator. Someone offers something on the table. The next negotiator either accepts or rejects it. If they accept it, it goes to the same offer, remains on the table, and goes to the next negotiator. And if it rejects it, it has now to offer a new one. Okay? And then this repeats until the negotiation ends. So if for the negotiation to end with success with an actual agreement, the number of agents that accepted must be equal to the number of agents minus 1. The 1 is the one who offered this out. So it's a very, very simple protocol. It's simple haggling what happens in a marketplace. And this protocol, I think, was proposed, the multilateral version in 2006 or something. And to the best of my knowledge, that is the last time an unmediated protocol was proposed. After that, we have some new protocols, but all of them are mediated, requiring third party, which we don't like. Okay, to build a negotiator for this protocol, you need to do two things. You need to be able to offer and to respond to offers. So at least you need to have what is called a bidding strategy and an acceptance strategy. And a very common structure for this type of agents is the OBA architecture. In this case, they add a third component called the opponent model, which is not required. Some agents don't have any opponent models, but you can use the opponent model to learn about your partner's utility function over the course of the negotiation. Notice that for this to be effective, your info contains some information about the partner utility function in advance. If it contains absolutely no information and the outcome space, you can't assume anything about it. For example, you can't assume smoothness on the utility function. And for discrete outcome space, for example, you can assume that all the utility of all outcomes are independent, completely independent. In this case, an opponent model is simply useless. You can't use an opponent model. So there are many strategies that work without opponent models, and the most common of them are the time-based strategies, in which you just, at every step of the negotiation, you have a level called an aspiration level. You offer things above it, and you accept things above it, but you don't offer below it, and then the aspiration level can go down over time until it matches your reserved value at the end of the negotiation. There's also tit for tat, very simple. Again, tit for tat has two versions, one with an opponent model, one without. The simplest form that's without an opponent model is, if you increase my utility, I will decrease it. Hopefully, we will agree near the middle. There are much better versions of that, but I'm not going into details. That's not the reason, the most important thing about this talk. All of these strategies in general do not have any guarantees of performance. The second component, the acceptance model, usually is very simple. And these are some of the most commonly used. Previous, if the opponent offers my last offer, I will accept. Anything else I will. And current, what I'm about to offer. If I receive what I'm about to offer, then I will accept it. And of course, there are other possibilities. I can have a threshold that goes over time. I can just use expectation over at the end of the time of the negotiation, but I need an opponent model. Okay, so that is what we have. We have the alternating offers protocol, and we have some strategies for it. The strategies I showed are the most simple, but there are many strategies. We have the AMAC competition that runs every year for more than 14 years now. So we have hundreds of negotiation strategies. Some of them are very good, but none of them have any guarantees. That is the main point. So now we want to introduce new protocols, so we want to be able to evaluate what should we look for. So the first thing is analyzability. Being able to say that's a good protocol or a bad protocol, I need to analyze it. And to analyze the protocol, I have the strategy. So if there is a strategy that is, we call DSEC, even though it is not really exactly the same as in auction theory, it means that a dominant strategy, a strategy that no one will deviate from, then I can analyze the protocol. I can assume that strategy and analyze the protocol. The other possibility is if the protocol has a good equilibrium. If I have a good equilibrium, perfect Belgian Nash equilibrium, then I can use this equilibrium assuming it will be right for analyzing the protocol. As we will see, for alternative offers, we don't have either of these. So that's why we can't analyze it. The second thing is efficacy, which means we want to know if the protocol achieving some requirements that we put. And the requirements we have are rationality. It means that the protocol never forces agents to accept irrational outcomes. Completeness, if there are win-win deals, it will be found. The protocol will find the win-win deals every single time. optimality, which means that all agreements are on the very front. And the last component, the last thing that I will not speak about much this time is revelation, which is something we want to minimize. We may achieve all of that by simply sharing our utility function in the first step. That's the protocol. You give me your utility function, or we give the utility function to a third party, they will calculate the Nash programming solution and give it to us. Okay? That's problematic because if we are willing to do the sharing, you wouldn't have non-negotiation at all. So we want to minimize the regulation. And one of the things about the protocol we are proposing this time is that it solves all of these problems, but it has very high regulation. But almost reveals your utility function by the end of the negotiation, which is crazy. Why are you negotiating? Efficiency is a less important thing, but you want the outcome space. You don't want to the outcome space is usually exponential in the number of issues you are negotiating about. So you want to be at least linear in the outcome space size. Otherwise, you have no chance of working in realistic scenarios. Multilateral complexity means how much you scale with the number of negotiators for multilateral negotiations. We can define all of these exactly given the description of a protocol that we defined before, or we can define each one of these requirements. And first we define something called an outcome perfect negotiation mechanism. It's a mechanism that has some implementable strategy assignment rules. So there is a way to assign strategies to agents that can be implemented by the agents themselves. So they can shoot them given the information they have that renders the protocol exactly rational, optimal, and complete. If that happens, we call the protocol an outcome perfect negotiation mechanism. Okay? And we can show that alternative offers is actually an outcome perfect negotiation mechanism. It is. But with very strange strategies that can never be used by anyone. No one will use these strategies. Why? Because they are not an equilibrium and they are extremely biased toward the first negotiator. The first negotiator gets the best result from this pair of strategies. And they are not creating an equilibrium, so they will not be actually correct. So a perfect negotiation mechanism is an outcome perfect negotiation mechanism in which the strategy assignment rule that we use is an equilibrium. So we can assume it will be played. And so that's what we want to achieve in this talk. So that's, in summary, what we have. If we look at information revelation on the x-axis and Pareto distance on the y-axis, the two factors that are most important here. So what we have for alternative offers, state-of-the-art strategies are in this area. So some high information revelation and unknown Pareto distance. All the protocols fall everywhere. It's not that every protocol is a point here. Almost every protocol is a whole cloud. Almost. What we are proposing is what we call the generalized bargaining protocol. It's an extension that covers a very large area of the space, and then you can try to find protocols within it. Then we introduce one we call tau, and the tau protocol achieves zero Pareto distance and other things. It's a perfect protocol with given our definition, but it has very high information revelation. So the research program is to just go in this direction. Try to reduce information revelation. You will lose guarantees, but how much can you achieve hiding of information while keeping most of the guarantees? So what's wrong with alternating offers? This is a very long list, but I would just focus on the two most important. In alternating offers, the first problem I'm calling the huddle depth problem. When you offer something, once it is, let's talk about the bilateral negotiation. If I offer you something and you accept it, the negotiation ends immediately. There's nothing else that can happen. So every time I offer something, I am a little bit worried. Would he accept it? It's very hard for me to explore. That's why usually you use conservative acceptance. The second problem is that there is no non-dominant strategy and no dominant strategy and no known good equilibrium. By good equilibrium, I mean an equilibrium that would expect people to play. Because the equilibrium we have, I can tell you what it means. The first negotiator becomes hard-headed. It's called strong He offers his best outcome continuously until the second negotiator starts to repeat offers. At this point, he starts to concede slowly, as slowly as possible. And if he hits his reserved value, he ends the negotiation. The second negotiator concedes immediately and keeps conceding forever. This couple of strategies is an equilibrium. Sorry, it's not an equilibrium. Randoms, yes.
I have a question. Sorry. Sorry to interrupt. I didn't know how to ask a question.
Okay.
I don't understand. Can you say something more about the sudden death problem? I got confused as to why conservative acceptance made sense. It felt to me you said you couldn't explore, so conservative offers, right?
Sorry, it is considering offers. Yes. That's what happens when you make your slides at 3 a.m. Yeah. Sorry. It's conservative. Yeah, that's true. It's conservative offering. Sorry. Yeah. And as we said, there are no guarantees on performance. It's extremely hard to reason about. Anybody knows about that? We tried a lot. It's extremely hard to reason about the protocol, even though it's very simple to specify. And it's computationally inefficient. That's what I will show empirically. It's too slow.
5 more minutes.
Yes, I finished very early. It's just a selling pitch, what I'm trying to do. I'll not give any details in this talk. I'll just try to convince you that this research program is meaningful. Okay, so that's what's good about the alternating offers. Simplicity, and that's what's bad. All guarantees. Okay. So, as we described before, our goal is to find a set of protocols and then find one of them that achieves good results, that are better than, and also achieve good guarantees compared with AOP. This is a generalized bargaining mechanism. It's very simple. It's as if you are running multiple threads of alternating offers in parallel. And to define it completely, you need to define 7 components. So I'll go over them very fast. How many offers can be offered in one step? So every negotiator can offer in its own thread a set of offers as a set of outcomes as an offer. Usually that's one. You can offer one thing. And then the response is how many can you accept at one step. And usually that's also one. You either accept or reject. But there are protocols we found protocols in literature that allow for multiple outcomes in a single offer. Then you have to define a graph for especially for multi-bounty negotiations, define a graph about who can send offers to whom, and define timing. Which agent can send at which time. These are defined by these 3 rules. Then this is the core of the protocol. The protocol consists of 3 main components. The filtering rule defines at every step for every negotiator what is the valid set of outcomes it can use, which can be a subset of the outcome space. That's decided by the mechanism, not the agent. Okay? The second thing is the update rule. The update for each thread, the mechanism keeps a subset called the tentative agreement tuple for this thread. And it has given a set of an offer and a set of responses. How should I update this tuple? That's called update rule. Finally, the evaluation rule. When does the negotiation end and what is the agreement? Based on the tentative agreement tuples. It cannot use any other information. Okay. So this decomposition into these 3 components actually covers a very large space of the design space we spoke about. And for the negotiator, it's almost the same as alternative offers. You need to have an offering policy and a selection policy, which is the acceptance policy, but we are calling it selection policy to allow for selecting from a set of offers, not just accept or reject. So that's the whole thing. What did we do? We just converted the X's into question marks. We can't prove anything. That's not a protocol. It's just a set of protocols. But then, that's not important. We can show that alternating offers is a very, very simple special case with a very simple evaluation rule. And then we can now complicate the selected bit and generate new protocols. So that is the new protocol we are going to generate. The changes from A to B are the following. Agents cannot repeat except the last offer. So I cannot repeat any offer I offered before, but I can repeat my last one. Once an agent starts repeating, it has to repeat forever. It cannot go back and offer anything new. Agreement is reached only if an outcome is offered and accepted by every negotiator. That's very different from AOP, in which it's offered by one negotiator and accepted by one. That is the sudden death problem. So that solves it. And the negotiation terminates if an agreement is reached or every agent is repeating, which means we exhausted the outcome. So that's a very simple protocol, and it can be specified very simply using the rules we have. It's not much more complex than alternative offers. And for it, we designed a very simple strategy, which is just for the selection policy, the acceptance policy, accept if an offer is better than what you accepted last. It's very simple. And for offering, offer outcomes in descending order of results. So that is only defined for discrete, finite discrete outcome spaces. And then reveal the last offer once you reach an outcome with a utility less than reserved value. So you don't go to irrational space. We can prove the following two theorems. The first one is that this protocol is a perfect negotiation protocol given our definition. Okay? And the equilibrium for it is SCS. It's this very simple strategy. The second theorem, which is the bad one, is that the negotiation will end in n steps with this specific outcome. We can define which outcome will be, we can find the outcome. But actually finding the outcome computationally, the fastest way to do it is to run SCS. That's the fastest way we could find to find this outcome. And this outcome is guaranteed to be on the Pareto frontier. That's very important. This is how this protocol works. Again, this is utility function of x, utility function of y. The agent starts from the top, its best outcome, and keeps conceding. Everything we can prove that every outcome on the Pareto frontier is accepted. Every outcome that is not on the Pareto frontier is rejected at some point. And the agreement is always in the Pareto frontier, and whenever it is in this quadrant, which is the things that are rational, it will be found. So this protocol is perfect, achieves everything we want. What is the problem? By the end of the protocol, you can almost recover the complete utility function of the agent. That's bad. Okay, so information revelation is very bad in this protocol. But that's not the final one, that's our first one. We just wanted to find something that's perfect. Then try to improve information revelation. These are examples of how it works against some other agents. I'm not going into these ones, but I can give you some of the gist of the results. When we do empirical evaluation against the best agents that we have, the best possible agents on the enough competition for alternative offers against this protocol. Our protocol is this one, and you can see in terms of fidelity, welfare is not shown, but it's the same. It achieves the best results, especially when the outcome, when the size of the rational set is small compared to the total size of the outcome space. And when it is a hard negotiation, this protocol shines. If it is an easy negotiation, everyone works well. Okay? But look at the number of rounds required. This is logarithmic. So these are the best agents from AOP, and this is where our protocol is. So it's much, much faster to reach agreement, even though it is an extremely simple protocol and an extremely simple strategy. And now we had almost everything except two, revelation and generality, because that works only for discrete outcome spaces, and our proof is correct only for bilateral negotiations. We conjecture that it will be correct for bilateral negotiation, but we don't have a proof. So that is what I want to tell you about today. So the conclusion is that it is possible to extend alternative offers to a more general form we call generalized bargaining mechanisms, while keeping its advantage. These mechanisms are specified by a small number of rules, simply 3 rules define that mechanism, which is not very far from an option, which is defined by 2 rules. And now we can actually start to get ideas from mechanism design into automated negotiation. That's our goal. We didn't do that yet. We did a very simple thing, which is introducing a very simple protocol and showing that this protocol has is perfect given our definition, and it has an equilibrium, which we cannot say about alternative offers. And it's unmediated. That's a very important point for us. So future directions is to evaluate tau theoretically empirically against SOTA. Actually, that was future until 3M. Again, that shouldn't be in the future work. Find an approximation that with better scalability and information revelation. That I think is the most important one. Or improve the protocol itself. Either improve the strategy or the protocol to achieve better scalability and less information revelation. And thank you. I'm sorry if I took too long.
I think we have time for one or two questions. Ask questions that can come up.
Hi. Can you say something more about the experiments? I didn't really understand how you used the AMAC competition because that was for a different, presumably the alternating offers protocol. So I didn't.
Yes.
Yeah. Okay. So I was just lost on how those agents would have made sense with your new protocol.
Yeah, they did it run in my new protocol. The comparison was of the combination of the protocol and the strategy. So I use alternative offers protocol here, AOP, with the best agents we know for AOP. Because we don't have an equilibrium. So that's the only thing I can do. Just find the best agents out there and use them. And I compare that with this strategy. Okay? So all agents are either using one of the state-of-the-art alternative overs strategies with alternative overs protocol, or they are using this very simple strategy with the tau protocol. And these are the results we get for that. The first experiment, we just used many agents, found the top two, and we run a much bigger experiment in which we used all the outcome spaces we found in the Genius platform. That's thousands. And some of them actually have, not all of them, all the ones that are less than 100,000 outcomes. We didn't use anything higher than that, and there are only few are higher than that. You know. So that's how we run it.
Time for one more question. Okay, so if we don't, I have a question. How much does this protocol rely on truthful participation, on the agent being truthful? And if it doesn't, how does it relate to the Myerson-Satterthwaite impossibility theorem?
Yeah. I had a slide about the impossibility theorem actually. I think it doesn't apply in our case for some reasons. First, it doesn't rely the protocol. The result we have assume truthful offering because SCS is actually truthful. It doesn't mean much what we define what is truthful in our case. It's just to offer you best outcome first and then concede. But other strategies can deviate from that. But there is no other strategy we could find that generates an equilibrium except truthful offering. That is much weaker than saying that truthful offering is dominant. I don't think it is dominant, but in this case, it is at least an equilibrium. So if I know that my partner is using SCS, there's no reason for me to deviate. And given that SCS is always on the Pareto frontier, and under the assumption, there is one assumption, if I assume that I have no information about the partner utility function, absolutely no information, then deviation from SCS for me can never improve that's what we could prove. Deviation from SCS for me can never improve my utility. The reason why this doesn't, why can we achieve that, given the impossibility result, is that the situation is slightly different in automated negotiation. Because you have this repetition. You are not trying to, it's not that you have evaluation, this result is in a single parameter case. You have evaluation and there is nothing better than truthful and you want to truthfully say your valuation, but in the same time achieve some accent. In this case, we don't have this situation exactly because we have multiple issues and we don't have a specific valuation for a single parameter that we're working against. So that's how it works. It doesn't assume truthful offering, but truthful offering is an equilibrium. We cannot show that it's the only equilibrium, but it is an equilibrium.
Okay. Thank you very much again.